Hello there. Welcome back to another journey through the cosmos. I'm so glad you're here with me tonight, settling in for what I hope will be the most peaceful drift into sleep you've had in a while. You know, there's something absolutely fascinating I want to share with you tonight, something that's been on my mind lately. Did you know that when a star is born, it doesn't just suddenly burst into light, like flipping a switch? No, it takes 10 million years. 10 million years just to turn on. Can you imagine waiting that long for anything? 10 million sunrises and sunsets passing by. Entire species evolving and disappearing. Continents drifting across the Earth, all while a star is still trying to figure out how to shine for the very first time. It's one of the most patient processes in the entire universe. And tonight, we're going to experience it in the most unusual way. We're going to drift backwards through time, starting with our sun, as it is right now, all grown up and glowing, then slowly, gently, rewinding through its memories. And you know, if you're finding some comfort in these cosmic stories, if my voice is helping you relax, even just a little bit, I'd be so grateful if you gently tap that like button. It really does help other sleepy souls find these journeys. And if you haven't already, maybe consider subscribing. That way you'll never miss another trip through the stars. I love reading your comments too, hearing about which cosmic wonders help you drift off. What mysteries of space bring you peace. But no pressure at all. We're just here together, floating through the universe. Everything else can wait. Now, let's get you really comfortable, wherever you are right now. Whether you're tucked into bed, curled up on the couch, or maybe even listening with your eyes already closed. Just let yourself sink a little deeper into that softness. Feel how the weight of the day is already starting to lift away, like you're becoming lighter, floating just slightly above all those earthly concerns. Take a breath with me, nice and slow, breathing in the quiet of space and breathing out any tension you've been carrying. That's perfect. And another one. Breathing in starlight, breathing out everything you don't need right now. Your body knows exactly what to do. It's been waiting all day for this moment, this permission to finally let go. Tonight's journey is going to be different from anything we've done before. We're not going to watch a star being born in the usual way, forward through time, from dust to light. No. Tonight we're going to do something special. We're going to start with our sun, as it is, right this moment, 4.5 billion years old, shining steadily above our world, even though it's nighttime where you are. And then we're going to drift backwards, sliding gently through the millennia, through the eons, watching our star unform, uncreate itself, moving in reverse through its memories until we reach that original cloud of dust and gas, that nebula where everything began. It's like listening to a story told backwards. But somehow, it makes even more sense this way. Because stars don't really think about their future when they're forming. They can't anticipate what they'll become. They just respond to the present moment, to gravity's gentle insistence, to the slow accumulation of heat. Each degree of temperature taking centuries to achieve, thousands of years passing between significant changes. We'll experience time the way a star does, where 1,000 years is just a heartbeat, where patience isn't a virtue, it's simply the only way things can happen. You'll feel the profound quiet of space, the kind of silence where you could wait 1,000 years between hearing any sound at all, where dust grains drift so slowly that generations of human civilization could rise and fall in the time it takes for two particles to meet. And we'll use temperature as our clock, our countdown, or rather, our count up from the absolute cold of empty space, minus 459 degrees Fahrenheit, absolute zero, slowly climbing, each degree representing not just heat, but time, centuries of waiting, millennia of patience, until finally, after 10 million years of counting, we reach that magic number, 27 million degrees, the temperature where hydrogen finally agrees to become helium, where a star finally gets to shine. But that's where we'll end. For now, we begin with light, with our beautiful sun as we know it, warm and golden and reliable, before we drift back through its memories, back through the millions of years of darkness that came before, ready to travel backwards through time with me, ready to remember how stars remember. Let's begin this gentle journey, this reverse lullaby through the cosmos. Let's begin our journey right here, right now, with the sun as it exists at this very moment, shining above us. Even though you can't see it from where you're lying, it's nighttime for you. But somewhere on Earth, it's always daytime, always bathed in that warm, golden light that's been flowing steadily for billions of years. Our sun is middle-aged now, about 4.5 billion years old, which means it's got another 5 billion years or so before it starts to change. That's the beautiful thing about stars like ours. Once they turn on, they just keep going and going and going, like the universe's most reliable nightlight. Right now, at this very second, deep in the sun's core, 15 million degrees hot, hydrogen atoms are fusing into helium. It happens so smoothly now, so effortlessly. 4 hydrogen atoms come together, and through a beautiful dance of physics, they become one helium atom, releasing just a tiny bit of energy. But when you multiply that tiny bit by the countless trillions of atoms fusing every second, you get all the light and warmth that makes life possible on Earth. Every second, the sun converts about 4 million tons of matter into pure energy. 4 million tons, just disappearing, transforming into the sunlight that'll reach Earth in about 8 minutes. Can you imagine that? The sunlight that warmed your face this morning. If you were outside today, that light was actually born 8 minutes before you felt it. It traveled 93 million miles through the vacuum of space, moving at the fastest speed possible in our universe, just to reach you, just to warm your skin. And that's just the journey from the sun's surface to Earth. The real journey. The one that takes much, much longer is the journey from the sun's core to its surface. You see, the energy created in the core doesn't just zoom straight out. No. It bounces around, gets absorbed, and re-emitted over and over and over. It can take a single photon of light, anywhere from 10,000 to 170,000 years, just to work its way from the core to the surface. Think about that. Light that's reaching Earth today might have been created when humans were still living in caves, or even before humans existed at all. The sun is playing the longest game imaginable, creating light that won't be seen for millennia. The sun's perfect balance right now is something to marvel at. Every second, gravity tries to crush it smaller, to compress all that mass into a tinier space. And every second, the pressure from nuclear fusion pushes back, trying to blow the star apart. But they're perfectly matched, like two equally strong people, pushing against each other, neither one winning, neither one losing, just maintaining this beautiful equilibrium that's been going on for billions of years. This is what a mature star feels like: settled, stable content. Let's drift a little closer to our sun in our imagination, but not too close, just close enough to really appreciate its size. You could fit about 1 million Earths inside the sun. 1 million. Try to picture that. If Earth was a marble, the sun would be a sphere about 3.5 feet across. That's bigger than a beach ball. And it's not solid like Earth. It's made entirely of gas, mostly hydrogen and helium, the two simplest elements in the universe, swirling and flowing in patterns. We're only just beginning to understand the surface we see, what astronomers call the photosphere. It's not really a surface at all, just the layer where the sun becomes transparent enough for light to escape. And it's covered in what look like bubbles, each one about the size of Texas, rising and falling every 5 minutes or so, like a pot of water that's been boiling for billions of years. These convection cells carry heat from deeper layers up to the surface, then sink back down to get reheated. An endless cycle, an eternal circulation. Now, let's begin to drift backwards. Let your mind relax its grip on the present. We're going to let time flow in reverse, like rewinding a cosmic movie. The sun starts to get just a tiny bit younger, a tiny bit smaller, a tiny bit cooler, though you'd never notice the difference over a human lifetime. or even 1,000 lifetimes. We're sliding back through the centuries now, through the millennia. The sun looks exactly the same. That's how stable mature stars are. They change so slowly that you need to rewind millions of years to see any real difference. 100,000 years ago, the sun still looked exactly like it does today. 200,000 years ago, still the same. 500,000 years ago, no visible change. This is the patience of stars. They measure time in millions, in billions. 1,000,000 years to a star is like a day to us, maybe even less. And we're rewinding through those days now, faster and faster, watching the calendar of deep time flip backwards. Now we're approaching 1,000,000 years ago. And finally, we can start to see the tiniest difference. The sun is just slightly smaller, maybe 1%, maybe less. Its temperature just a hair cooler, though still far too hot for us to comprehend. But here's where things get interesting, because as we continue backwards from here, the changes are going to start accelerating. The further back we go, the younger and smaller our sun becomes, until we reach that crucial moment, that first flash of sustainable fusion, when our star finally figured out how to shine. 1,000,000 years ago, our sun had only been properly shining for about 9 million years. It had just graduated from its long preparation, like a student who spent a decade in school just to learn how to read. The fusion reactions were still stabilizing, still finding their rhythm. The star was like a newborn, taking its first steady breaths, no longer gasping and sputtering, but breathing smoothly, confidently, ready for the billions of years ahead. The space around our young sun was different too. The planets were all formed by now. Earth was here, though very different than today. Mars was here. Jupiter, Saturn, all in their orbits. But there was still more debris, more asteroids, more comets. The solar system was like a house, where the furniture had been delivered, but not quite arranged yet. Everything was finding its place, settling into the patterns we know today. Let's pause here for just a moment. Floating in space, 1,000,000 years ago, watching our sun shine with its new light. Can you feel how different time is out here? How 1,000,000 years doesn't feel that long when you're thinking in stellar terms. We've only just begun our journey backwards. We still have 9 million years to go. 9 million years of darkness and patience and slow preparation. As we prepare to dive deeper into the past, to rewind further through our star's memories, notice how your breathing has naturally slowed, matching the rhythm of cosmic time. Every breath you take represents thousands of years passing, or rather, unpassing, as we drift backwards. Your heartbeat, each pulse, could be a century. Each pause between beats, a millennium of patience. The sun, at 1 million years old, was like a child who just learned to walk, sure of its new ability, but still remembering what it was like to crawl, to struggle, to fall. And that's where we're heading next. Back into those struggling times. Those millions of years of darkness before the light. We're going to continue rewinding, faster now, sliding back through the eons, like sliding down a gentle slope into the past, into the time before our star knew how to shine. Can you feel yourself getting lighter as we drift further from the present? Time doesn't weigh as much out here, in the depths of space, in the depths of the past. Everything moves like honey, slow and smooth and golden, even though we're moving backwards through millions of years. It feels like floating, like drifting, like the most natural thing in the universe. Now we're sliding back, even further, past that 1 million year mark. And something remarkable is happening to our sun. It's starting to flicker, not visibly to our eyes, but in its core. The fusion reactions are becoming less steady, less reliable. We're approaching the very beginning of our star's true life. That moment, when it first achieved sustainable nuclear fusion, when it stopped being a protostar and became a real star. At about 900,000 years ago, our sun is stuttering. It's like watching someone trying to start a campfire. Sometimes it catches, burning bright for a few thousand years. Then it dims again, not quite hot enough, not quite dense enough. The core temperature hovers right around 26 million degrees, sometimes 27, sometimes dropping back to 25. Each degree represents tens of thousands of years of heating or cooling. The star can't quite decide if it's ready. This is the most delicate phase in a star's life. Like a butterfly emerging from its chrysalis. If the temperature drops too much, fusion stops completely, and the star has to wait, accumulating more mass, compressing more, heating up again. But if it gets just hot enough, if it crosses that magic threshold and stays there, then the star wins. Fusion becomes self-sustaining, and the long, stable life of a main sequence star begins. Let's drift back another 100,000 years, 800,000 years ago. And our sun definitely isn't shining steadily yet. It's pulsing, breathing, like a giant heart made of gas and plasma. Each pulse takes centuries. Expansion, contraction, expansion, contraction. The star is trying to find its balance, that perfect equilibrium between gravity pulling inward and fusion pushing outward. Sometimes gravity wins for a while, and the star shrinks, getting hotter, denser. Sometimes fusion wins, and the star swells, cooling slightly, losing pressure. Can you imagine having a heartbeat that lasts 100 years? Boom, a century passes. Boom, another century. That's how our young sun is breathing. And we're watching it in reverse, watching each breath get more labored, less certain, as we drift back toward the time before fusion, before light. 700,000 years ago, 600,000, 500,000. The temperature in the core is dropping as we go backwards. 25 million degrees, 24, 23. Each degree lost represents thousands of years of cooling in reverse, or rather, each degree we lose going backwards represents thousands of years it took to heat up going forwards. The atoms in the core are moving slower, colliding less frequently. Fusion happening only sporadically. At 500,000 years ago, our sun is what astronomers call a T Tauri star, named after a star in the constellation Taurus that's going through this phase right now. It's not quite a baby and not quite an adult. It's like a stellar teenager, moody and unpredictable. Sometimes bright, sometimes dim, throwing tantrums of stellar wind that blow away any remaining dust and gas nearby. These stellar winds are fierce, even though the star isn't properly shining yet. They're powered by magnetic fields and convection, by the churning, twisting motion of all that gas. In forward time, these winds cleared out our solar system, blowing away the last wisps of the nebula we were born from, creating the relatively empty space between planets that we see today. But we're watching it in reverse. So the winds are bringing material back. The space around our young sun is getting dustier, foggier, more crowded. 400,000 years ago, and the fusion in the core is barely happening at all. Just occasional bursts when conditions are just right. When enough hydrogen atoms happen to collide with enough force. The core temperature has dropped below 20 million degrees, still incomprehensibly hot by human standards, but not quite hot enough for sustained fusion. 300,000 years ago, 200,000, 100,000 years before our sun truly turned on. We're deep in the protostar phase now. The sun exists. It's round. It's massive. It's hot. But it's not a true star yet. It's living on gravitational energy alone. Getting hot purely from compression, from the weight of its own gas, pressing down, down, down. This is like watching someone trying to light a match in slow motion, extreme slow motion, where each attempt takes millennia. The match is there, the striker is there, but the motion isn't quite fast enough. The pressure isn't quite right. So the star waits and compresses and heats and waits some more. Now we're at that crucial moment, the boundary, the transition. We're watching the very last successful fusion reaction before the star truly ignited. Or rather, the first one, since we're going backwards. A handful of hydrogen atoms in the core, moving just fast enough, colliding just right, creating helium and releasing energy. But it's not enough. to trigger a chain reaction. Not enough to create the runaway fusion that makes a star shine. It's like seeing the last spark before the fire goes out, or the first spark before it catches, depending on which direction you're watching from. The core temperature is hovering right at 20 million degrees, the absolute minimum for any fusion at all. And as we continue backward, we're about to cross below that threshold into the truly dark years, the millions of years when our proto-sun was just a ball of collapsing gas, heating up through compression alone, patient as only gravity can be patient. Now, let's drift back 5 million years, and everything changes. We're firmly in the protostar phase now. Our sun is huge, maybe 2 or 3 times its current size, but much, much cooler. The core temperature is only about 10 million degrees, half what it needs for fusion. And it's glowing, but not from nuclear fire. It's glowing from gravitational energy, from the heat of compression, like how a bicycle pump gets warm when you compress air. 5 million years before our sun turned on, it was already the dominant object in our solar system. It contained 99% of all, the mass, just as it does today. But it was a gentler giant, softer, puffier, more spread out. The gas wasn't packed as tightly. The pressure wasn't as intense. It was like a sleeping giant, gathering its strength, preparing for the long performance ahead. The planets were already forming around this proto-sun. Earth was probably mostly assembled, a ball of molten rock, slowly cooling. Jupiter was greedily gobbling up gas, growing fat and massive. Saturn, too. The rocky inner planets were being bombarded constantly by asteroids and comets, each impact adding a little more mass, a little more material. The solar system was like a construction site, dusty and chaotic and violent, but with the framework already in place. Our proto-sun at this age was rotating much faster than it does today. Maybe completing a rotation in just a few days instead of the 27 days it takes now. But it was slowing down, always slowing down. Its magnetic field grabbing onto the surrounding disk of gas and dust like a brake, transferring angular momentum outward, getting slower and more dignified with each passing millennium. The temperature is everything in this story. It's the clock, the countdown timer, the measure of progress. 5 million years before ignition, the core was at 10 million degrees. 4 million years before, maybe 12 million. 3 million years before, perhaps 15 million. Each degree took centuries to achieve, thousands of years of patient compression, of gravity doing its slow, inexorable work. Imagine trying to heat something up using only gravity, no fire, no electricity, just the weight of gas pressing down on itself. It's the slowest heating method in the universe, but also the most reliable. Gravity never gets tired. never gives up, never takes a break. It just pulls, constantly, patiently, for millions and millions of years. As we drift deeper into the past, the proto-sun gets larger and cooler, more diffuse, less organized. 6 million years before ignition, 7 million, 8 million, the core temperature drops below 5 million degrees, below 3 million, approaching the temperature of the surface of today's sun. Still hot enough to vaporize any known material, but nowhere near hot enough for fusion. The proto-sun at this age is like a slowly tightening fist. Each year, gravity pulls a little harder, compresses a little more. The gas particles fall inward, speeding up as they fall, converting gravitational potential energy into kinetic energy, into heat. It's the universe's way of storing energy, banking it up over millions of years, preparing for the moment when there's finally enough to trigger fusion. 9 million years before our sun turned on, and we're almost back to the beginning. The proto-sun is enormous now, or rather then, maybe 10 times its current width, but so diffuse you could almost call it a thick cloud rather than a star. The core temperature is below 1 million degrees, still hotter than anything on Earth, but cool by stellar standards. Everything moves so slowly here, waves of pressure taking centuries to cross from one side to the other. Sound itself, if there was any sound in space, would take years to traverse this bloated protostar. We're in the realm of true cosmic patience now, where nothing happens quickly, where every change is measured in millennia, where the universe operates on a timescale that makes human life seem like less than a blink. 10 million years before our sun ignited, we've reached the very beginning of its story. Or rather, we're approaching the beginning as we drift backwards. The proto-sun barely exists as a distinct object now. It's more like a denser region within a vast cloud, a place where the nebula has started to thicken, to notice itself, to begin the long collapse that will eventually birth a star. The temperature here is almost nothing, maybe a few thousand degrees in what will become the core, cooler than lava on Earth. The gas is so spread out that if you could somehow stand in the middle of it, you wouldn't even know you were inside a forming star. It would just seem like empty space, maybe slightly hazier than usual, like the faintest fog on a clear night. Except this fog extends for billions of miles in every direction. Let's drift even further back, past that 10 million year mark, into the time before our sun was even a protostar, when it was just part of a nebula, a vast cloud of gas and dust floating through space. This is where we enter the realm of true cosmic silence, true cosmic patience, where 1,000 years can pass between interesting events. The nebula that would become our sun was enormous, light years across, containing enough material to make thousands of stars. It was mostly hydrogen, the simplest element, created in the first few minutes after the Big Bang, mixed with a little helium and just a tiny seasoning of heavier elements, what astronomers call metals. Things like carbon and oxygen and iron, the ashes of previous generations of stars that lived and died before our sun was even a possibility. In this nebula, 12 million years before our sun would shine, the density is almost nothing. Maybe a few hundred atoms per cubic centimeter. That's emptier than the best vacuum we can create on Earth, so empty that atoms rarely meet, rarely interact, just drifting through the darkness, occasionally catching a photon of distant starlight, warming up by a fraction of a degree, then cooling again. The silence here is profound, absolute. If you could somehow exist in this nebula and wait, and wait, and wait, you might hear the faintest whisper of a collision once every 1,000 years. Two hydrogen atoms finally meeting after eons of drifting, bumping together with less force than a falling feather, then bouncing apart to drift for another 1,000 years before meeting anything else. Can you imagine that kind of solitude? Floating in darkness for a millennium, between conversations, between touches, between any interaction at all. That's the normal state of matter in a nebula. Profound isolation, each atom essentially alone in the universe, unaware that it's part of something larger, something that's very, very slowly coming together. But even in this emptiness, gravity is working. Every atom, every grain of dust pulls on every other particle. The pull is incredibly weak, weaker than you can possibly imagine. But it never stops, never rests. And over millions of years, these tiny pulls add up. The nebula starts to develop patterns, currents, places where the gas is slightly thicker, slightly thinner. 15 million years before our sun ignites, and the nebula is almost perfectly uniform. Just the slightest variations in density. Ripples so faint, they're barely there. But these ripples are seeds, the beginning of structure, the first hint that something might form here. And we're watching these ripples smooth out as we go backward, watching the nebula become more and more uniform, more and more peaceful. The temperature throughout the nebula is near absolute zero, maybe 10 degrees above. That's about minus 440 degrees Fahrenheit. So cold that atoms barely move, just the slowest drift, like motes of dust in a perfectly still room. Except the room is light years across, and the motes are separated by distances that dwarf our entire planet. Sometimes a grain of dust, a tiny speck of carbon or silicon, maybe a tenth the width of a human hair, begins a journey that will take 1,000,000 years. It starts at the outer edge of what will become our solar system and begins to fall so slowly you couldn't possibly see it move, toward the slightly denser region at the center. Each year, it falls inward by maybe a few thousand miles, less than the distance across America. In a human lifetime, it barely moves at all. In 1,000 lifetimes, it's gotten maybe halfway to its destination. Let's follow one of these grains, a tiny speck of carbon, created in the death throes of some ancient star. Billions of years ago, it's been drifting through interstellar space for eons, and now it feels the faintest pull, something calling it inward. It doesn't know it's going to help build a star. It doesn't know anything. It just responds to gravity's whisper, beginning its slow spiral inward. 20 million years before our sun ignites. This grain of carbon is still at the outer edge of the nebula. It'll take 5 million years just to reach the region where Jupiter will eventually form. Another 5 million to get to where Earth will be. And then 10 million more to finally reach the center, to become part of the proto-sun, to contribute its tiny mass to the growing collection. Along the way, this grain might collide with another grain once every 100,000 years or so. Sometimes they stick together, held by the weakest of electrical forces, forming a slightly larger grain. Sometimes they bounce apart, each continuing on their separate journeys. These collisions are so gentle, so slow, like two snowflakes meeting in perfectly still air. The nebula has its own chemistry happening, incredibly slowly, molecules forming when atoms happen to meet, water ice condensing on dust grains when the temperature is just right, methane, ammonia, simple organic molecules, the building blocks of the building blocks of life, all forming at a pace that makes glaciers look fast. As we continue drifting backward through time, 25 million years before ignition, 30 million, the nebula becomes more and more diffuse. The region that will become our sun spreads out over a larger and larger volume, or smaller and smaller as we go backwards. The dust grains are farther apart, the gas more evenly distributed. We're approaching the time when this nebula itself was born, when some distant event, perhaps a supernova explosion, sent ripples through space that started the whole process. But let's pause here for a moment, floating in this near-perfect vacuum. This is what most of the universe looks like. Not stars, not planets, but vast, empty spaces with just the faintest trace of matter. And yet, from this almost nothing, given enough time, enough patience, stars are born. Every star you see in the night sky started like this, as a region of slightly denser gas in a nebula, waiting millions of years to collapse, to heat up, to ignite. The grains we're following, each one has its own story, its own journey. This one might have been part of a planet around another star billions of years ago. That one might have been forged in the first generation of stars after the Big Bang. They're all converging, slowly, patiently, toward a common center, like raindrops flowing toward the sea, except each drop takes millions of years to complete its journey. Some grains are magnetic, tiny compass needles, pointing in random directions. As they drift and tumble, they create the faintest magnetic fields that will eventually become the sun's powerful magnetism. But for now, are weaker than the magnetic field of your brain as you drift towards sleep. These magnetic fields help guide other particles, creating invisible channels through space, highways for matter to follow. Though the traffic moves at a cosmic crawl, we can use temperature as our clock throughout this whole process. Starting from near absolute zero in the cold nebula, minus 450 degrees Fahrenheit, and counting up so slowly. Each degree represents thousands of years, tens of thousands, as gravity does its patient work. Minus 400 degrees. That's 100,000 years of collapse. Minus 300. A million years have passed. Minus 200. Several million years of waiting. By the time the temperature reaches minus 100 degrees Fahrenheit, still colder than Antarctica, the nebula has been collapsing for maybe 10 million years, and we're only just getting started. The temperature needs to reach millions of degrees before fusion can begin. Each degree fought for, earned through eons of compression. The mathematics of this heating is beautiful in its simplicity. As the cloud contracts, gravitational potential energy converts to kinetic energy, to heat. The amount of energy is enormous, but it's spread over such a vast volume and released so slowly that the heating rate is almost imperceptible. A few degrees per million years, like trying to boil water by breathing on it. Except eventually, given enough time, it works. In the regions where planets will form, different processes are happening. Ice is condensing, melting, recondensing. Minerals are clumping together, forming pebbles, rocks, boulders, eventually planetesimals, each collision adding heat, adding mass. The whole solar system is assembling itself from dust, grain by grain, pebble by pebble, with a patience that's almost impossible to comprehend. Now let's follow individual grains even more closely. Let's become one with them as they drift through the cosmic darkness. Pick one grain, just one. A speck of silicon, perhaps, smaller than the smallest thing you can see. This grain has been traveling for 50,000 years already, spiraling inward from the outer reaches of the nebula, and it still has another 50,000 years to go before it reaches the center, before it becomes part of what will one day be our sun. Watch how slowly it moves. If you could film its journey and speed it up 1,000,000 times, it would still look like it was barely moving, just drifting, tumbling, occasionally catching a photon of starlight and warming by a billionth of a degree, then cooling again in the darkness. The grain doesn't know where it's going, doesn't know it's part of something magnificent, being born. It just follows the gentle tug of gravity, inward, always inward, patient, as only a grain of dust can be patient. Every century or so, this grain passes close to another grain, close being relative. They might miss each other by thousands of miles, but in the vastness of the nebula, that counts as close. Their tiny gravitational fields interact, bending their paths ever so slightly, a cosmic dance in extreme slow motion. Sometimes they're heading for a collision, but it'll take 10,000 years to actually meet. 10,000 years of approaching slowly, slowly, like two people walking toward each other from opposite ends of a continent. When grains finally do collide, it's the gentlest touch imaginable, softer than a snowflake landing on your eyelash, softer than a whisper. They might stick together, held by the weakest electrical forces, or they might bounce apart, each continuing their separate journeys for another 1,000 years. These collisions are building blocks, each one adding a tiny bit of mass, a tiny bit of complexity to the growing structure. Some grains are special. They carry water ice, frozen so solid, it's harder than rock. These ice grains are like little seeds, attracting other molecules, building up layers, growing from specks to pebbles over millions of years. Each layer takes centuries to accumulate, like the world's slowest growing pearl. Other grains are made of carbon, the element of life, forged in the hearts of dying stars. These carbon grains have been through so much already, created in stellar furnaces, blasted into space, drifting for billions of years, and now finally finding a new home, becoming part of a new star system. Their journey is almost over. Just another few million years to go. Let's watch a particularly interesting grain, one made of iron, one of the heaviest elements that can be made in regular stellar fusion. This iron grain is like a little time capsule, carrying the memory of a star that died maybe 5 billion years ago. It's been circling our galaxy ever since, waiting for its chance to become part of something new. As it falls inward through the nebula, it's picking up speed, very, very gradually, starting at maybe a few inches per second, less than walking speed. After 1,000 years of falling, it might be moving at a few feet per second. After 1,000,000 years, maybe a mile per hour. The acceleration is so gentle, you'd never feel it, but it never stops. Constant, patient, inexorable. This iron grain is special for another reason. It's magnetic. It creates the tiniest magnetic field around itself. And as it tumbles through space, This field interacts with the magnetic fields of other grains. They align slowly over millions of years, creating larger magnetic structures, invisible rivers of magnetism that guide other particles. These magnetic fields are like ghostly highways through the nebula, channels that matter prefers to follow. The grain passes through regions of different temperature, different density. Near the center of the collapsing cloud, it's getting warmer, maybe up to a few hundred degrees above absolute zero. Still incredibly cold, but warm enough that some molecules start to become active, start to vibrate, start to interact in new ways. Chemistry is happening, slowly, so slowly. Water molecules forming when hydrogen meets oxygen, taking centuries for each molecule to assemble. Methane forming when carbon meets hydrogen, ammonia, formaldehyde, even simple amino acids, the most basic building blocks of life, all forming at a pace that would try the patience of mountains. Let's count the grains as they accumulate. 1 grain, 2 grains, 1,000 grains, each one taking its own path, its own time. After 1,000,000 years, maybe 1,000,000,000,000 grains have collected in the central region. After 2,000,000 years, 1,000,000,000,000. Numbers so large, they lose meaning. But each grain matters. Each one adds its tiny contribution to the growing mass. By the time 5,000,000 years have passed, the collected grains in the center equal the mass of Jupiter. By 8,000,000 years, they equal the mass of 100 Jupiters. By 10,000,000 years, approaching the mass of our sun, all from individual grains, each one invisible to the naked eye, each one taking millennia to complete its journey. Some grains never make it to the center. They end up in the disk, surrounding the protostar, the disk where planets will form. These grains have their own destinies. Some will become part of Earth, part of the rocks beneath us, part of the water in our oceans. Some will become part of Jupiter or Saturn. Some will remain as asteroids, comets, cosmic wanderers. Every atom in your body, except for the hydrogen, was once a grain drifting through that nebula. Iron in your blood, calcium in your bones, carbon in your DNA, all of them took this same patient journey, spiraling inward for millions of years. And here's something beautiful to drift off to sleep with. Some of those atoms might have traveled together, been companions for millions of years before becoming part of you. The grains are still falling as we speak, or rather, as we dream. In stellar nurseries throughout our galaxy, throughout the universe, grains are making their patient journeys, each one taking centuries, millennia, eons to reach their destinations. The universe is in no hurry. It has all the time there is. Now let's use temperature as our cosmic clock, counting up from the absolute bottom, from the coldest possible temperature, where atoms barely move at all. This is our starting point, in the nebula, minus 459.67 degrees Fahrenheit, absolute zero. We can't actually reach absolute zero, even in the emptiest parts of space. It's a few degrees warmer, but let's start our count from there anyway. Minus 459 degrees. The nebula is just beginning to notice itself. Gravity is just starting its work. Minus 458 degrees. 1,000 years have passed. Grains are starting their inward drift. Minus 457. Another 1,000 years. The collapse is so slow. You'd need godlike patience to notice. Minus 450 degrees. 10,000 years of gradual warming. The grains are picking up speed, ever so slightly. Minus 440 degrees. 100,000 years have passed. The nebula is definitely collapsing now, though still so slowly. Minus 400 degrees. 500,000 years of patient gravitational work. Each degree represents so much time, so much patience. Minus 350 degrees. That's 1,000,000 years of collapse. Minus 300 degrees. 2,000,000 years. The temperature is climbing so slowly, like watching a glacier melt. One molecule at a time. By the time we reach minus 200 degrees Fahrenheit, still colder than the coldest place on Earth. 3,000,000 years have passed. The nebula has contracted significantly. The central region is getting denser, hotter, beginning to look like something that might one day become a star. Minus 100 degrees, 5,000,000 years of collapse. The protostar is definitely forming now, a distinct object within the nebula. Still far too cold for fusion, but warming, always warming. Minus 50 degrees, 6,000,000 years. 0 degrees Fahrenheit, 7,000,000 years have passed. Now we're in positive numbers, but still so cold. 100 degrees Fahrenheit, 8,000,000 years of gravitational compression. It's taken 8,000,000 years just to reach the temperature of a hot summer day. 200 degrees, 300, 400. Each 100 degrees representing hundreds of thousands of years. 1,000 degrees Fahrenheit. 9,000,000 years have passed. The core of the protostar is now hotter than any oven, hot enough to melt lead, but still nowhere near hot enough for fusion. We need to reach millions of degrees. We're not even 1% of the way there. 10,000 degrees, 9.5 million years. The core is now hotter than the surface of the sun will eventually be. Atoms are moving faster, colliding more often, but still not hard enough to fuse. 100,000 degrees, 9,900,000 years. We're getting close to the 10,000,000 year mark. 1,000,000 degrees, 9,990,000 years. The protostar is so close to ignition, but still not quite there. the temperature needs to climb another 26 million degrees. Each degree fought for, earned through compression, through patience, through the inexorable pull of gravity. 10 million degrees, 9,999,000 years. Almost there, almost. The hydrogen atoms in the core are moving so fast now, slamming into each other with tremendous force, but still not quite enough. They bounce off each other's electrical fields, repelling like magnets with the same poles. To fuse, they need to get close enough for the strong nuclear force to grab hold. And that requires even more speed, even more heat. 15 million degrees, 9,999,900 years. The collisions are getting more violent, more frequent. Occasionally, very occasionally, two hydrogen nuclei get close enough to feel the strong force, but they don't quite stick. They need just a little more energy, just a little more heat. The star is like a runner approaching the finish line, so close. But every step forward is harder than the last. 20 million degrees. This is the threshold, the minimum temperature, where fusion can begin to happen. Not consistently, not sustainably, but occasionally, randomly. Two hydrogen nuclei collide with just the right speed, at just the right angle, and for the briefest moment, they stick together. They begin the process of becoming helium, releasing a tiny burst of energy. But it's not enough to heat the surrounding gas, not enough to trigger more fusions. The reaction dies out, and the star has to wait for the next random success. 25 million degrees, 9,999,999 years. The fusion reactions are happening more frequently now, every few seconds, somewhere in the core. But they're isolated events, like raindrops before a storm. Each fusion releases energy, heating the gas nearby, making the next fusion slightly more likely. It's a feedback loop that's trying to establish itself, trying to become self-sustaining. 26 million degrees. The star is right on the edge, balanced on a knife's blade between success and failure. If it can just get a little hotter, compress a little more, the fusion will become self-sustaining. But if it loses too much heat, if the pressure drops, it'll have to start over, have to compress for more, millions of years. 27 million degrees. And suddenly, it happens. The fusion reactions reach a critical threshold. Each reaction triggers more reactions, which trigger more, a chain reaction of nuclear fusion that spreads through the core. The star has finally learned how to shine. After 10 million years of patient preparation, 10 million years of slow collapse, of gradual heating, of waiting, the star ignites. But let's understand why it takes so long. Why stars can't just turn on immediately. It's all about probability, about the laws of physics, about the fundamental forces that govern our universe. You see, hydrogen nuclei are protons, and protons have positive electrical charges. Like charges repel each other. It's one of the basic rules of electromagnetism. The closer two protons get, the stronger they push each other away. It's like trying to push two powerful magnets together with the same poles facing. They resist, they repel, they refuse to touch. But there's another force, the strong nuclear force, that wants to pull protons together. This force is much stronger than electromagnetism, but it has a catch. It only works at incredibly short distances. The protons have to get within about a femtometer of each other. That's a millionth of a billionth of a meter. Closer than close. They have to practically touch. So we have this cosmic challenge. Protons need to get close enough for the strong force to grab them. But the electrical force is pushing them apart the whole way. It's like trying to roll a ball up a hill that gets steeper and steeper near the top. Most of the time, the ball rolls back down. Only when the ball is moving fast enough, when the temperature is high enough, can it make it over the peak and down the other side. Temperature is really just a measure of how fast particles are moving. At 27 million degrees, hydrogen nuclei are moving at about 600 miles per second. That's fast enough that when they collide head-on, they can overcome the electrical repulsion. Get close enough for the strong force to take over and fuse into helium. But even at this temperature, it's still rare. Most collisions still result in the nuclei bouncing apart. In fact, any individual proton in the sun's core might wait billions of years before successfully fusing. Billions of years just waiting for that perfect collision. But there are so many protons, about 10 to the 57th power of them, that even though each individual fusion is rare, the total number of fusions per second is enormous. About 400 million tons of hydrogen fuse every second in our sun. This is why stars need to be so massive, so dense, so hot. If a cloud of hydrogen is too small, it'll never reach the temperature needed for fusion. It'll compress and heat up to maybe 1 million degrees, maybe 10 million, but not the 27 million needed for sustained fusion. These failed stars become brown dwarfs, cosmic embers that glow from gravitational heat, but never truly shine. Our sun was just massive enough if it had been a little smaller. If the original nebula had contained a bit less material, we'd have a brown dwarf instead of a star. Earth would never have formed. Or if it had, it would be a frozen ball of ice in eternal darkness. The physics of fusion is beautifully precise, unforgiving. There are no shortcuts, no way to speed up the process. Gravity needs time to compress the gas, Compression creates heat. Heat enables fusion. But each step takes millions of years. It's the universe's way of ensuring that stars don't just flash into existence and burn out immediately. They have to earn their light through patience. And here's something beautiful. Once a star achieves fusion, it remembers how. The reactions become self-sustaining, self-regulating. If the core gets too hot, fusion speeds up, creating pressure that expands the star and cools it down. If it gets too cool, fusion slows, pressure drops. Gravity compresses the core and heats it back up. It's a perfect thermostat, keeping the star stable for billions of years. This stability, this balance, was 10 million years in the making. Every degree of temperature fought for over millennia. Every atom of hydrogen carefully collected from the vastness of space. Every grain of dust contributing its tiny mass to the growing whole. The star's first light is a triumph of patience, a monument to the slow, steady work of gravity. Now, let's experience that moment, that first sustainable fusion from the inside. You're in the core of the protostar. It's been dark for 10 million years, not the darkness you know, not the darkness of night, but a deeper darkness, the darkness of a place where light has never been. The pressure is unimaginable, the weight of 1,000 Earths pressing down from every direction. The temperature has been climbing slowly, steadily, for eons, and then, in a space smaller than a city, it begins. The first sustained fusion reactions. 4 hydrogen nuclei coming together through a complex dance of particle physics. 2 protons collide, and one transforms into a neutron, releasing a positron and a neutrino. This new deuterium nucleus finds another proton, forms helium-3. 2 helium-3 nuclei meet and create helium-4, releasing 2 protons back into the mix. Each reaction releases energy, photons of light. But these photons don't escape immediately. They're trapped, absorbed and re-emitted countless times, beginning their own journey that will take hundreds of thousands of years just to reach the surface. But that's another story, another kind of patience. For now, in this moment, the star has won. It has achieved fusion. It has become a true star. The energy from fusion creates pressure, pushing outward against gravity's pull. For the first time in 10 million years, gravity has an opponent, an equal. The collapse stops. The star finds its balance, its size, its shape. It's like watching someone take their first breath after holding it for an eternity. The star expands slightly, contracts, expands again, finding its rhythm, learning to breathe with nuclear fire. This moment, this first light, sends ripples through the surrounding space. The stellar wind begins, pushing away the remaining gas and dust of the nebula, clearing the neighborhood. revealing the new star to the universe. Any planets that have formed are suddenly bathed in light for the first time. Their surfaces begin to warm. If they have atmospheres, weather begins. If they have water, it starts to cycle, evaporating, condensing, creating the possibility for chemistry, for complexity, eventually, perhaps, for life. Our journey backward has brought us to this moment, or rather, from this moment. We've traveled in reverse from the stable sun we know, back through millions of years of darkness, through the patient accumulation of mass, through the slow spiral of countless dust grains, to arrive at the beginning, the moment when our star first opened its eyes. And now, as you drift deeper towards sleep, you can carry this patience with you, this cosmic patience that measures time in millions of years, that builds stars from dust, one grain at a time, that waits 10 million years just to create light. There's no rush in the universe, no hurry. Everything happens when it's ready, when the conditions are right, when enough time has passed. Let's drift even deeper now into understanding this patience, into the very mathematics of waiting, into why the universe insists on taking so long with everything it does. You see, there's a beautiful truth hidden in the physics, a reason why stars must wait 10 million years, why they can't rush, why patience isn't just a virtue in space. It's the only way anything happens at all. Think about the forces involved. Gravity is the weakest force in the universe, so weak that you overcome it every time you lift your hand. Every time you stand up, a tiny magnet can pick up a paperclip, defeating the gravitational pull of the entire Earth. And yet, given enough time, enough mass, enough patience, gravity builds stars, builds galaxies, shapes the entire cosmos. It's the ultimate example of slow and steady winning the race. The strong nuclear force that powers fusion is the opposite. It's incredibly powerful, 100 times stronger than electromagnetism, but it only works at distances smaller than an atomic nucleus. It's like having incredible strength, but arms so short you can't reach anything. The protons have to get so close, so impossibly close. And getting them that close requires tremendous energy, tremendous heat, which requires tremendous patience. There's an equation, a beautiful, simple equation that describes this. The rate of fusion depends on temperature to the fourth power. That means if you double the temperature, fusion happens 16 times faster. But here's the catch. To double the temperature through gravitational compression takes millions of years. You can't rush gravity. You can't make mass fall faster than physics allows. Everything has its own pace, its own rhythm. The universe seems to have these speed limits built in everywhere. Light can only travel so fast. 186,282 miles per second, no faster. Heat can only flow so quickly, from hot to cold. Gravity waves ripple through space, at the speed of light, no quicker, and a collapsing cloud of gas can only compress so fast, only heat up so gradually. It's as if the universe is saying, slow down, be patient, everything will happen in its time. Even inside atoms, patience rules. When two protons get close enough to fuse, they don't instantly become helium. First, one proton has to transform into a neutron through beta decay, and this is incredibly rare. On average, a proton in the sun's core will wait 10 billion years before successfully completing this transformation. 10 billion years just waiting for the right quantum moment, the right random fluctuation. And this is happening at 27 million degrees. Any cooler, and the wait would be even longer, maybe infinite. This is why smaller stars burn slower and live longer. A star half the mass of our sun might take 20 million years to ignite and then burn for 200 billion years. A star twice our sun's mass might ignite in only 5 million years, but burn out in just a billion. The universe rewards patience with longevity. The slower you start, the longer you last. The red dwarf stars, the smallest true stars, will still be shining. Trillions of years from now, long after our sun has faded away. And it's not just stars. Everything in space happens slowly. Planets form over millions of years. Mountains on Earth take millions of years to rise. Continents drift at the speed your fingernails grow. Even the faster processes are slow by human standards. A supernova explosion, one of the most violent events in the universe, takes months to fully unfold. The universe doesn't know how to hurry. Let's feel this slowness in our bones, in our breath. Each breath you take right now, in and out, might represent 1,000 years of stellar time. Your heartbeat, steady and patient, might be counting out centuries. The gentle electrical pulses in your brain as you drift towards sleep. Each one could be a year passing in our story of stellar formation. The mathematics tells us something profound. The time it takes for a star to form is proportional to the square root of its density divided by gravity. This is called the free fall time. It means that no matter how massive the cloud, no matter how strong the gravity, there's a minimum time required. You can't compress it faster. You can't skip steps. The universe has rules, and those rules require patience. Think about the energy involved. Our sun converts 4 million tons of matter into energy every single second. But it took 10 million years to store up enough gravitational energy to start that process. That's like saving pennies for 1 million years to buy something that costs $1. Except once you buy it, it keeps paying you back forever. The patience of stars is an investment that pays dividends for billions of years. And here's something beautiful to fall asleep to. Every photon of sunlight, every bit of warmth you felt today is possible only because of that 10 million year wait. If stars could form instantly, if they didn't require that patience, they'd burn too hot, too fast. They'd flash and die before planets could form, before life could evolve, before consciousness could emerge to wonder about it all. The 10 million year delay is a gift. It's the universe's way of ensuring stability, of making sure stars don't just flash into existence and disappear. It's like a cosmic quality control process. Only the gas clouds that can sustain themselves for 10 million years get to become stars. Only the patient inherit the cosmos. Now let's return one more time to that moment of first light. But let's experience it as the star remembers it, as a memory played forward this time. After our long journey backward, the star remembers the darkness, the endless darkness that came before. It remembers being cold, so cold, just a few degrees above absolute zero. It remembers the first stirrings of gravity, the first time two particles noticed each other across the void. It remembers beginning to spin, slowly at first, as the cloud contracted. Conservation of angular momentum, another patient law of physics. As the cloud got smaller, it spun faster, like an ice skater pulling in their arms, but happening over millions of years. The star remembers forming a disk, the disk where planets would eventually form. Material spiraling inward, carrying angular momentum outward, everything finding its balance through patient negotiation with physics. It remembers the temperature climbing, degree by degree, each one fought for over millennia. From near absolute zero to millions of degrees. The star remembers the first time two hydrogen atoms fused in its core. Not the sustainable fusion that would come later, but the very first one. A preview of what was possible, a promise of what would come if it just kept compressing, kept heating, kept waiting. The star remembers the frustration, if a star can be frustrated, of being so close. But not quite there. 20 million degrees, 25, 26, almost hot enough, almost dense enough. Like trying to light a fire with damp wood, sometimes a spark, sometimes a flicker, but not quite catching. Not yet, not yet. Just a little more time, a little more pressure. And then, finally, after 10 million years of trying, the star remembers, succeeding. 27 million degrees. The fusion becomes self-sustaining. The darkness ends. Light begins its journey outward, first trapped in the dense core, bouncing from atom to atom, taking hundreds of thousands of years to reach the surface, but eventually, inevitably, emerging as the first true starlight. The star remembers that moment as a triumph, as a graduation, as a birth. All that patience rewarded, all that waiting justified, It had earned its place in the cosmos, earned the right to shine. And it would keep that light burning for billions of years, a monument to patience, a testament to the power of taking your time. This is the memory we've been traveling through, the memory of our own sun, played in reverse and now forward again. The memory of transformation from cold cloud to nuclear furnace, from darkness to light, from patience to triumph. And as you drift deeper towards sleep, you're carrying this memory with you, this cosmic patience, this understanding that the best things, the brightest things, take time. Your breathing has slowed to match the rhythm of stellar time. Each exhale releasing days, months, years. Each inhale drawing in the patience of the cosmos. You're floating now in that space between waking and sleeping, where time moves differently, where a moment can feel like hours, where hours can pass in an instant, just like in space, where time is flexible, patient, undemanding. And now, gently, softly, we begin to return from our journey through stellar time. We've traveled so far together, backward through 10 million years, forward again through patience and physics. We've felt the weight of gravity, the slowness of cosmic processes, the incredible patience required to create light from darkness. And now, it's time to let all of that knowledge settle into your bones, into your dreams, into the quiet spaces of your mind. Our sun continues to shine right now, even in your darkness. It's there, on the other side of Earth, warming other dreamers, lighting other paths. The same patient star that took 10 million years to ignite. Now reliable, steady, constant. It'll shine tomorrow, and the next day, and for billions of days to come. All because it learned patience, learned to wait, learned that the universe rewards those who take their time. You've witnessed something tonight that few ever truly understand. The deep time of stellar formation, the patience of physics, the slow dance of gravity and gas. You've counted up from absolute zero, degree by degree, each one representing centuries of cosmic patience. You've followed individual grains of dust on million-year journeys, watched them spiral inward, contribute their tiny mass to something magnificent. The story we've shared tonight lives in you now, part of your understanding, part of your dreams. When you wake tomorrow and see sunlight, if you see sunlight, you'll remember 10 million years. That's what it took. 10 million years of darkness before the light. And somehow, knowing this makes the light even more precious, even more beautiful, even more worth savoring. And if you're still awake, still floating here with me in the cosmos, that's perfectly okay. There's no rush, no hurry, just like those dust grains taking their sweet time, spiraling inward. You might still be listening to my voice, still drifting through these cosmic stories, still waiting for sleep to fully claim you. And you know what? If you'd like to continue this journey, there's another story waiting for you. Maybe you'd like to hear about black holes and how they bend time itself, or the dance of galaxies slowly waltzing through the void, or perhaps the patient formation of planets from swirling disks of dust. There's always another cosmic story, another journey through space and time. Just let the next video play. No need to move, no need to open your eyes. Let YouTube's gentle algorithm be your guide to the next adventure. The universe has endless patience, and so do we. If you're still conscious enough to hear this, still aware enough to understand, you could let another of these stellar sleep stories carry you even deeper, each one designed to slow your thoughts, to quiet your mind, to remind you of the vast patience of the cosmos. You don't have to do anything. Just let it happen. Let the next story begin when this one ends, like one dream flowing into another. But whether you continue on or whether you're already deep in sleep, know that you're always welcome here, always welcome in these quiet spaces between the stars, where time moves like honey, where patience is the only currency, where 10 million years can pass in the space between heartbeats. Thank you. Thank you for joining me on this backwards journey through time, for witnessing the patient birth of our star, for understanding why the universe takes its time with everything important. Your presence here makes these stories worth telling, makes the cosmos feel less vast, less lonely, more like home. You've been such a perfect traveling companion tonight, so patient yourself, listening to the slow accumulation of degrees, the patient journey of dust grains, the million-year processes that built the star that lights our world. And now, you've earned your rest, earned your dreams, earned the right to let go completely and drift wherever your sleeping mind wants to take you. Maybe you'll dream of floating through that ancient nebula, watching dust grains dance in slow motion. Maybe you'll dream of being inside a star as it first ignites, feeling that triumph of patience rewarded. Maybe you'll dream of time itself, stretching and compressing, moving like the universe moves, without hurry, without urgency, just flowing. The star's memory is your memory now. The patience of the cosmos flows through your dreams. 10 million years of waiting, all leading to this moment, to you, here, now, made of stardust, breathing stardust, dreaming stardust dreams. You are the universe, understanding itself. And tonight, you understand patience, deep patience, cosmic patience. Every atom in your body, except hydrogen, was forged in a star. Every one of them waited millions of years to be created, billions of years to find their way to Earth, to find their way to you. You are made of patience, built from patient processes, held together by forces that never hurry, never rush, just exist, moment by moment, eon by eon. So rest now, truly rest. Let your mind slow to the speed of stellar formation. Let your thoughts drift like dust grains through the void, taking their time, finding their way. No need to think about tomorrow or even tonight. Just be here in this eternal now, this patient present, where 10 million years and 10 seconds feel the same. Sleep is calling you, the way gravity called those dust grains. Gently, patiently, inevitably. You can resist for a while, like those grains drifting at the edge of the nebula. But eventually, in time, you'll spiral inward toward dreams, toward rest, toward the warm center where consciousness transforms into something else, something quieter, something deeper. The numbers are fading now. The temperature counts. The millions of years, all becoming soft and blurry like distant stars. All that remains is the feeling, the deep, patient feeling of cosmic time, of universal processes that cannot be rushed, of the beautiful slowness that builds stars, builds worlds, builds you. Close your eyes, if they aren't already closed. Feel the weight of stellar time pressing gently on your eyelids. Feel the patience of the universe in every relaxed muscle, every slowed breath, every quieted thought. You've learned the secret tonight, that the universe makes its greatest creations slowly, carefully, patiently. And you are one of those creations made of star stuff, thinking star thoughts, dreaming star dreams. Good night, my patient traveler. Good night, child of the stars, keeper of cosmic memories, witness to the slow birth of suns. May your dreams be filled with the gentle drift of dust grains, the patient accumulation of light, the slow, beautiful processes that built everything you've ever known. May you sleep with the patience of a forming star, deeply, peacefully, for as long as you need. Sweet dreams, stellar dreams, patient dreams. The cosmos is holding you now, rocking you in its ancient rhythms, singing you the lullaby of time itself. Rest now, rest and remember. 10 million years to make a star, but only a moment to make a dream, and both are equally magical, equally patient, equally perfect. Good night. Sleep well. Dream deep.